Now we are going to move to the whole world to be explained to you by Brian Greene. And Brian will be interviewed by Walter Isaacson, as you know, the CEO of the Aspen Institute, my former editor at Time, who will be tempted to edit my introduction.
Hey, Mark. Thank you. And the universe parts. The fabric of the universe unfolds. Brian Greene has written The Fabric of the Universe, the Fabric of the Cosmos, The Elegant Universe, Icarus on the Edge of Time, which I love, and The Hidden Reality, the trio of books that deal with multiverses, the fabric of the cosmos, relativity. We are supposed to, within 20 minutes, actually 18 minutes and 17 seconds, give you the whole story of the cosmos and the universe. So, Brian, let's begin at the beginning. How did it begin?
How did it begin? Good question. We don't know.
But
we have some ideas.
And the idea is that it expanded.
Yeah, so the most refined idea, which is by, in my opinion, no means confirmed, is an idea called inflationary cosmology, which tries to answer a somewhat more refined version of the question, how did it begin? What was it that caused space to start swelling in the first place? We all believe that the universe is expanding. The observations support that. What got the expansion started? And the inflationary theory says that gravity itself is the culprit, because even though the gravity that we're familiar with in everyday life is attractive, pulls things together, Einstein's theory, which you wrote extensively about, shows that in certain exotic circumstances, gravity can be repulsive.
So you have a repulsive force that at the very beginning pushes things out. Does it create space and time as well as particles and matter?
It's, again, a hard question, but our best answer at the moment is that space and time needed to exist already for this phenomenon to take place. But what inflation does is it leverages the pre-existing space and time, which could be a tiny little nugget, and turns it into a large cosmos. So it basically takes space and time as an input, very small, yields big space and time and matter and energy as the output.
So if time already existed when this happened, what happened the day before this happened?
Yes, I knew you were going there, which is why I played defense here and said I don't know 5 times already in the first 2 minutes. So we don't know, but we have ideas, right? So one possibility is that the notion of before is a concept that doesn't actually make sense when it comes to the beginning of the universe. A good analogy is, think about the concept of heading northward on Earth, right? So if you're heading northward, you pass by someone, you say, point me in the direction of further north. They point, you continue to walk. You pass somebody else, same question, they point you in the northward direction. But when you get to the North Pole itself, if you ask somebody there, how do you go further north? They look at you sort of oddly, quizzically. The notion of going further north than the North Pole doesn't make any sense.
So going back in time doesn't make any sense.
That's right.
Yeah.
So at the beginning of time, just like the North Pole, that may be where the concept of time only comes into play, and there's no notion of before when it comes to the beginning.
How do we get from general relativity to figuring out, both mathematically and theoretically, the notion of a Big Bang?
Well, that's an exciting and curious story. Einstein himself, after he fashioned the equations of general relativity, which people can read the wonderful history of in your book, he started to apply the theory to a variety of circumstances, the orbit of Mercury being one famous one, the bending of starlight by the sun. But he also noted that if you applied the equations to the whole universe, it gave rise to an unfamiliar, unexpected result, which is that the fabric of space itself should be stretching or contracting. The universe couldn't be static. And that cut against the philosophical perspective of the time, including Einstein. So Einstein changed the equations to ensure that that result wouldn't come out, that the universe could be unchanging on the largest of scales. Then, fast forward to 1929, when Edwin Hubble turns a powerful telescope to the sky and sees that the distant galaxies are all rushing away. The universe is expanding. Einstein kind of euphemistically smacks himself in the forehead and says, why did I change the equations when I could have predicted this amazing fact about the universe just from my own mathematics?
Yeah, he calls it his biggest blunder. So then they walk the cat backwards, that if it's expanding, they say, well, it had to have all been in this single point. Right?
That's right. You basically, in the hands of really a Belgian priest, was the first person to really articulate this most precisely, a guy named Georges Lemaitre. He used Einstein's math, the face value math, not the math that Einstein mangled to meet his own philosophical prejudice. He uses a math to turn the cosmic film in reverse, and the universe gets smaller and smaller and smaller, and therefore he comes to a primordial nugget from which everything would then emerge. He called it the primordial atom. And the name Big Bang, that came later on. I think it was a radio interview. I think it was with Fred Hoyle, who was a critic of this theory and was talking about it on the radio. And he said, the Big Bang. You know, it's this like derogatory description. But, of course, it's the name that stuck. And it's our best understanding of how things started.
And you mentioned that Lemaitre and others get to it by walking the mathematical equations. It's sort of what you do. I don't think people actually know that you're also a professor of mathematics. And in some ways, mathematics is now your guidepost to figuring out is how physical reality is. So is that where math sort of takes over and becomes the guide of physics?
Yeah, I mean, I'd say the one lesson that we've learned since Isaac Newton is that for reasons that we can't fully yet understand, math seems to be the right language for describing phenomena in the universe. Math is the shining light that can illuminate the dark corners of reality that we've not been able to access directly, right? We can't literally see the beginning, but we can use the math to peer back using the equations to get some understanding of what happened at the beginning.
But don't we need to, at some point, have some evidence from physical reality?
No.
But what about the cosmic...
No, we do. No, it's absolutely crucial, and and without that, we're just sort of speculating. And the evidence comes from so many places. So first, Einstein's mathematics makes predictions about things that we can directly access, like the bending of starlight by the sun, which was tested in 1919 during a solar eclipse. And just as Einstein predicted, the stars were slightly shifted in the sky because of the sun's presence. And you know the story well, but perhaps not everybody does. Einstein then gets a telegram alerting him that his ideas had been confirmed through the observation, and somebody asked him, Professor Einstein, what would you have said if the data showed that the theory was not confirmed? And he said, I'd be sorry for the dear Lord because the theory is correct. Yeah. So this is how certain he was of these ideas. But that's just one example. When it comes to cosmology and the Big Bang, we can use the equations to make predictions for how much residual heat should be left over from the Big Bang today, the so-called cosmic microwave background radiation. And we can make predictions on how the temperature of that heat should vary from one location in space to another. And then we can do measurements, and the measurements agree with the theoretical predictions to fantastic accuracy. And that is a breathtaking confirmation that this mathematics is not just speculation, that the math is actually aligning with how the world works.
Give me an example of that measurement of the cosmic background radiation. I mean, they go to the North Pole or South Pole?
So there are many ways to access it. You can access it through satellite-borne telescopes, such as the WMAP experiment, the Wilkinson background radiation probe, which has done a fantastic job at measuring the microwave background radiation, the microwave anisotropy probe. But the more recent one, I think is the one you're referring to, is the so-called BICEP-2 experiment down at the South Pole, where for 3 years, a team of astronomers pointed this telescope at a patch of the southern polar sky and extracted information about the microwave background radiation that, again, bears out a yet more subtle prediction of the theory.
And this is radiation that actually emanated from the bang.
Yes. So in the beginning, it was hot, right? Really hot. And as the universe expanded, the heat was spread out. It diluted. And it cooled down. and you can calculate how cold it should be today, and it's about 2.7 degrees above absolute zero. So that's the temperature of deep space, not when there's sources like stars nearby, but if you're in deep empty space, that's the temperature. But you can go one step further and not just calculate the average temperature, you can calculate how the temperature should vary from place to place, and the math shows that it should vary by on the order of 1/100,000th of a degree, a tiny variation. And you can do these very precise measurements and indeed see the temperature variation in just the pattern that the mathematics predicts.
What do you mean when you call something the fabric of the cosmos?
It's a hard question. Is space really a thing, or is it just a useful concept in order to organize our perceptions of reality? You're over there. You're further away in space. The table is yet further. Is space merely the vocabulary that allows me to articulate locations, or is space really a thing? And nobody fully knows the answer to that, but in Einstein's general relativity, and different people interpret it differently, I see space as a thing in Einstein's theory.
Space meaning the fabric of space and time together.
That's right. Space and time are stitched together in Einstein's special relativity.
And they would exist even if nothing else existed?
That's right. That's right. And there's been a lot of debate about this. You know, if you were to remove everything from space, the moon, the sun, Earth, everything, what would be left? Would you have an empty universe that still has space and time, or would you have nothing? I mean, a good analogy is if you take an alphabet, right, and you start to remove the letters, Z and X and A and B, when you remove that last letter, what's left? Is it like an empty alphabet? Not really. It's like nothing, because the alphabet comes into existence with the letters that make it up. Is that true of the universe? Does it come into existence only when there's stuff populating it, or can there be an empty stage called space-time that would exist even in the absence of matter? I think it's the latter.
There's a wonderful thought experiment which you deal with in, I think, your first book, Newton's bucket.
Yes.
Explain how that helps you think that there is a fabric of space.
Yeah, so this is a thought experiment that Isaac Newton came up with when he was trying to understand, basically, if space was a thing. And he imagined taking a bucket and filling it with water. And he noted that as you spin the bucket, the water climbs up the sides of the bucket. So I think, you know, even kids do this at the beach, right? You spin it around and it climbs up the sides.
What we would call inertia.
That's right. So the water has some intrinsic quality called inertia that causes it to resist that motion, and when it resists, it kind of gets pushed out, it goes up the sides. So he imagined doing that in a completely empty universe. Now, there's some issues about that because gravity is part of what makes the shape. So he actually imagined now taking two stones, same idea, connecting them by a rope and spinning them around. Would the rope pull taut? And to Newton, it was obvious that the rope would pull taut, even in empty space. And therefore he said, what is the rope and rock spinning with respect to? There's nothing there. There's no earth, no sun, no anything. Therefore, the rope and the rocks must be spinning with respect to a something called space. Space itself must be setting the benchmark, the reference, with respect to which that motion is happening. Others then came along and said, no, we disagree. You remove everything from the universe and you take your little spinny rock and, you know, ropey thing, and it's not going to pull taut. It'll just kind of stay completely limp. And it's still an issue that people debate.
Is there any evidence we could find one way or the other?
It's very hard to remove everything from the universe, right? I mean, that's kind of what you'd like to do. So what you do is you try to find alternate implications of one perspective or another. And I would say as today, most people, I haven't done a survey, but I suspect that most people would say it would pull taut, that space-time does set the reference frame for a certain kind of motion, accelerated motion, but there are others who are holdouts and disagree with that.
What did we learn from the Large Hadron Super Collider?
We learned a lot. We learned how to build the biggest experiment that our species has ever embarked upon. These are really, you know, the fantastic temples of the 20th, 21st century. They are our pyramids in a sense. But in terms of the science that we have extracted, the most important thing is the discovery of the Higgs boson, the Higgs particle. I think most people have probably heard something. I mean, people know about this Higgs idea, right? So there was this particle that was predicted mathematically in 1964 by Peter Higgs and many others who really deserve equal credit for it. But it was just a mathematical idea that was a solution to a puzzle. How do particles get mass? How do they resist being pushed when you want to speed them up or slow them down? And the idea was space is filled with a kind of molasses-like substance called now the Higgs field, like a steam bath that we don't see that's all around us.
And that gives mass to particles.
That's right. As particles try to move through the steam bath, this cosmic molasses, they experience, roughly speaking, a kind of resistance-like drag force. And that
what
is
is
their
the
heft.
relationship of the Higgs field to the fabric of space-time?
Well, if the Higgs idea is correct, there'd be virtually no distinction between them. This substance would fill every nook and cranny of space, and in a sense it would be unremovable unless somehow you could recreate maybe the temperatures of the very early universe. So the analogy that I think sort of captures that idea is, if I don't know, do you have any tattoos? Okay, well, good. I don't know where you were looking, and I am not going to ask. But imagine that you start to have more and more tattoos. And ultimately, if you cover your entire body, then the distinction between your skin and the tattoo becomes kind of meaningless. You are the illustrated man at that point. You're completely covered with tattoos. Similarly, space is completely filled with this Higgs stuff, and if you can't remove it, there's almost no distinction between space and the stuff that fills it.
What if they hadn't found it and they had found that there is no Higgs field? Does the entire standard model of quantum theory go out the window?
Well, that would have been far more exciting for a theorist. Less exciting, for Peter Higgs and others.
Would we have lost mass and lost weight?
Well, I don't think the universe cares much about our understanding of the universe, so it would have shrugged it off and said, silly little humans. But a wonderful thing as a theorist, we would have been sent back to the blackboard to answer these deep puzzles. Where does the heft of the fundamental constituents come from? That would have been enormously exciting for an idea that we thought was the answer to be proved wrong. There sometimes is a misperception that physicists or scientists more generally get stuck on an idea and they become so wedded to it that they'll hold on to it even in the face of evidence that suggests the contrary. No, it's completely the opposite. We love it when ideas that we cherish are proved wrong, because that's the biggest opportunity of a lifetime to try to come up with the next new idea that will take its place. Now, in this example, it was a wonderful triumph of mathematics and experiment where the idea was confirmed.
Now, mathematics has led you to superstring theory, of which you're very associated. Explain why the math led you there.
Well, since the 1960s and 70s, people have tried to put together Einstein's ideas of gravity, the general theory of relativity that we've been talking about, together with another theory, the theory of the small ingredients, quantum mechanics. And
By
it
the
turns
way,
out,
Einstein tried, on his deathbed, he was doing that.
Well, sort of. Einstein was trying to put gravity together with electromagnetic theory to build a unified theory, thinking that he could do an end run around the uncomfortable features of quantum mechanics he didn't like so much. So he was hoping in some sense to go this way and then do that to quantum mechanics. But that seemed not to really work out. So we are trying the more straightforward approach of putting gravity and quantum theory together. And the standard model of particle physics, which predicted the Higgs particle, hugely successful, is unable to put gravity and quantum mechanics together. That leads us to this new approach, which at least on paper, superstring theory does put gravity and quantum mechanics together.
Is there anything coming up in the next 5 or 10 years that you would say would help give you a physical test of what you're doing there?
No.
Okay.
Yeah, I wish the answer, I can go speculative here, which may be speculation on speculation, which is always an uncomfortable place to be. But just to say, we don't believe any of these ideas until they make predictions that we can test. So let's be real clear here. If you ask me, do I believe in string theory? The answer is absolutely no. I never have and I never will until there is experimental data that supports it. Having said that, it is the most promising and, I have to tell you, mathematically compelling approach to putting gravity and quantum mechanics together, and that's an important puzzle to solve. That drives us to continue working on it. In the best of all worlds, when they turn the Large Hadron Collider back on in 2015, is it possible that some of these ideas will make contact with observation? Yeah, it's possible. We could see evidence of extra dimensions. That's one of the other features of the theory. Particles slam together, some of the debris can get knocked out of our dimensions according to the math. We would recognize that by a loss of energy. People are looking for this. We could see a whole class of particles called supersymmetric particles, which the theory predicts that we haven't yet seen. We could see microscopic black holes that would decay into a spray of other particles. So all of these things are possible, but I don't like to place hope on them in that I consider them long shots. Mm-hmm. So when they don't come through, I don't want it to be, hey, you guys predicted that that was going to happen, and then it didn't. No. It's possible, but unlikely.
Is it inevitable in superstring or string theory that there are other universes?
It's not inevitable. It is one of the very controversial developments over the last 10 years.
But you believe it's true?
Again, believe is a funny, funny word. So do I believe in other universes? Absolutely not. Do I find it a compelling possibility, and can I see how the math naturally suggests it, and does that compel me to work on it? It does. But until there's observation or experimental support, I don't believe anything.
And I guess Einstein once said that one of the grand questions was, did the good Lord have a choice in the way he invented the universe? Explain that and answer it for us, or for Einstein.
Yeah. So Einstein asked a very important question, which is, could the universe have been otherwise? Could the mass of the particles be different? Could gravity have behaved differently? Did the Lord have a choice, or is somehow that dictated by logic and mathematics alone? And we don't know the answer, but if these ideas of other universes are correct, then it's completely opposite. It may be that every possibility is played out on the grand landscape of reality. So rather than having one unique universe, it might be all possible universes. The truth is probably somewhere in between.
We've run out of time, but let me hit you with a couple of quick things.
Sure.
One of which is, why does this all matter?
Well, if you ask my mom, it doesn't, right? You know.
She wanted you to be a doctor.
Yeah,
not
exactly,
a PhD,
right? So
yeah.
it gives her a headache and all that kind of stuff. But I think it helps many people get a sense of how we fit into the larger picture, how we're part of this spectacular cosmos. And I don't consider it making us somehow small and insignificant, although we are, but take into account these little tiny creatures walking around on the surface of the earth can figure out what happened a billionth of a billionth of a billionth of a second after the beginning and what things will be like 100 billion years into the future. That to me is this amazing story. So that is the most exciting drama of discovery we've ever been engaged with. That's why it matters.
And for people who want to hear more, there's the World Science Festival that you and Tracy Day, your wife, is doing, and World Science University. Give it a quick pitch.
Yeah, so World Science U is a new online platform that we at the World Science Festival have developed to try to get these ideas out to the general public, but not just at the level we're talking about here, which is interesting and exciting, but the real math behind it in a highly produced, highly visual way. So if you like relativity or this kind of stuff, check it out. It's a fun way to learn.
Just Google World Science University
World Science U,
and Brian Greene. Yep. And the festival is when?
May 28th to June 1st. We have
and you
50
can buy
events.
tickets?
You can buy tickets. They just went on sale, although a few things are already sold out. But 50 events around the city that will allow you to immerse yourselves in science.
Brian, thank you.
Thank you.